So we're almost done with chapter 8. There's just a few loose ends I want to tie up. I did go slightly, I went through chapter 8 in a slightly different order than before. But what I want to do is I want to think about another way to categorize the different singularities that we talked about in this chapter. So I'm going to call this a proposition. And I'm going to leave it mostly as something just for you to do on your own. But let's let F be holomorphic on a region G with in isolated singularity Z naught. Okay, Z naught is some element in G. Okay, so let F be holomorphic in a region G, let Z naught be an isolated singularity. Then Z naught is a removable singularity. We talked about definitions, but this is just kind of a bunch of equivalent ways to think about kind of how these definitions all fit together. So then Z naught is a removable singularity if either f of z is bounded on G except at Z naught. That's equivalent to saying that the limit is z approaches Z naught of f of z exists. And it turns out that that's equivalent to saying that the limit of z minus Z naught times f of z is 0. Okay, this part C will make sense when we talk about a few of the other terms here. Z naught is a simple pole if the following happens. Let's let L be the limit as z approaches Z naught of z minus Z naught times f. So if L exists and is non-zero, then Z naught is a simple pole. And moreover, this limit, the reason why we wrote this to begin with, this limit turns out to be the residue. Okay, I'll prove, I'll talk a little bit about this at the end here. Okay, so I'll give kind of a sketch of a proof for number 2, or at least part of number 2. Number 3, Z naught is a pole of order at most k if the limit of z minus Z naught to the k times f of z exists. Okay, so if that limit exists, then this means that Z naught is a pole of order at most k. On the flip side, Z naught is a pole of order at least k if there exists a function g on the region capital G except at Z naught, where f of z is equal to g of z over z minus Z naught to the k. Okay, for all z in G except at possibly Z naught. Okay, so that means that you must have a pole of order at least k if that happens. Okay. Yeah, that's really all I have to say there. The reason why I just hesitated there for a second, because I just want to mention the reason why it's a pole of order at least k is that maybe G itself has a singularity at Z naught. Okay, we're not excluding that, because all we're saying is that G is some nice function on this set where we remove Z naught. So maybe it has a singularity there. Maybe it doesn't, but that's why it's got to be a pole of order at least k. And then for number 3, it's a pole of order at most k if this limit exists. Okay, so if it's a pole of order say, yeah, so if you were to have here's a good example. If you were to take a simple pole, that's a pole of order 1, and that happens when this limit exists but it's not equal to 0. And so if you were to put, say, a 3 here at this exponent, this limit would be 0, and therefore z naught would be a pole of order at most 3 according to number 3. Okay, according to part 3 here. So this whatever exponent, so if this is a 7, this would be a pole of order at most 7. Now it's a simple pole, it's pole of order 1, but it's still a pole of order at most 7. So that's why we get the bounds there. So anyway, so that's the idea, and that's how that works. Let me just prove a little bit with number 2. Number 2 is going to be the one that we're going to use over and over and over and over, and I'll explain why soon. Okay, so simple poles and particularly calculating residues, this will be super helpful for us for reasons that we'll see shortly in chapter 9. Yeah, here's the idea. So let's say that we have a function f, and we have a Laurent series. Let's say that it has a simple pole at z naught. So what that means is that you can write f as b1 over z minus z naught plus all the a terms. Okay, and so on. Now, let's look at the limit of z minus z naught f of z as z approaches z naught. That's going to be the limit as z approaches z naught of b1 plus a0 time, all the rest time. Let me actually just write it nicely like this. Z minus z naught times the infinite sum as n goes from 0 to infinity, a sub n, z minus z naught to the n. Now, here, if you plug in z equals z naught, you're going to end up with 0. Okay, so no surprise there. Here, this b1 is non-zero. So this limit is going to be b1. And this b1 is non-zero because what we said ahead of time is that f has a simple pole of order 1, right? Or it has a simple pole, meaning a pole of order 1. And therefore, b1 is going to be the non-zero. Okay, so in this case, 1 is the largest integer where b sub n is non-zero. In this case, b1 is non-zero. So that means that automatically this limit won't be 0, and b1, which is this limit, happens to be the residue. Okay, so that'll be super, super useful for us. The converse basically holds. If you take a Laurent series and then you think about what it means for the limit of z minus z naught times f to be to exist and to be non-zero, that means that f must be of this form. And therefore, b1 is going to be the residue again. Okay, and so you have a simple pole of order 1. Excuse me, that doesn't make any sense. You have a simple pole, which is a pole of order 1, and b1 is the residue. Okay, so the converse follows basically by the same idea of looking at the Laurent series and thinking about what does it mean for this limit to exist and to be non-zero. It means that f must be exactly of this form. Okay, so a little bit hand wavy. I'm not going to go over the rest of it, but that's really it. Okay, and this will be super useful for us.